Okay, in this video, we're going to discuss the Phasor relationship between the series RL circuit and then series RC circuit and then series RL and C circuit. Now, first, let's discuss about the series RL circuit. The voltage for the series RL circuit is the vector sum of the resistive voltage and then the inductive voltage. Now, in our previous video, when we look into the purely resistive and then purely inductive load, we came across that for the purely resistive load, that current and voltage are in same phase, and then for the purely inductive load, current was lagging the voltage by 90 degree. Now, in case of the series RL circuit, the resultant voltage will be the vector sum of this resistive voltage and then the inductive voltage, and their phase difference will be between 0 to plus 90 degree. Let's check about the phasor diagram with the circuit diagram here. Now this is the circuit diagram. We have supply voltage V, and then you have the load R and L, which is in series, are connected. So for the voltage at the resistor R is given by VR, and then for the voltage at inductor is given by VL. If you draw the phasor diagram for the VR and the VL, it looks like this. VR at the 0 degree, because in a purely resistive load, this VR is in phase with the IR. And then in case of purely inductive load, your IL is leading, not that your VL is leading the IL by 90 degree. Now, to find the resultant voltage for this R and L series connected circuit, this is the resultant voltage. So this one you can get it with the vector sum of this VR and then IL, and whatever is this angle, it will be within this 0 to 90 degree. Now, if you apply the parallelogram here, this section, the length of this one will be same as this VL, right? So we are transferring it here. In this base, we are writing VR, height we are writing VL, and then this the hypotenuse is our resultant voltage for the series RL circuit. So VR is given by I times the resistance, and then VL is given by I times the reactance here, the inductive reactance. And then this, if we again combine this R and XL, you'll get this, the value Z. This Z is called the impedance in our electrical language. Now this hypotenuse is called the impedance. Now the resultant voltage of the series RL circuit is given by I times this impedance. Now from this voltage angle, okay, this angle is called the voltage angle. Now from the voltage angle, we can also derive the impedance angle. See here in the base we are writing R, and here we are writing the reactance, be it capacitive or the inductive. This side will be our the reactance, amplitude, magnitude of the reactance, and then this resultant is called the impedance. Now remember this angle, okay? Now this is the voltage angle, and here we have the impedance angle. Now from the voltage angle, if you apply the Pythagoras theorem, so the resultant voltage V will be equal to root of VR square plus VL square. And then to find the phase angle or the phase difference between phase difference between the RL circuit, here we can calculate tan theta is equal to VL by IR. So you can make this theta as a subject. So we have to take tan inverse of VL by IR by using the trigonometric ratio. Also from the impedance triangle, we can calculate Z using the Pythagoras theorem, and then we can also calculate the angle. So angle you can also calculate from this directly from the impedance, that reactance and the resistance, or you can also use with this trigonometric ratios. So now this one is for the series R and L circuit. Now let's look for the okay, before we look into the another topic, we have numericals here. We can try to solve it. You simply have to substitute the given parameters in the formula that we have. Okay, now the series RC circuit. The same thing. This supply voltage is connected in series with the R and C. They are also in the series. So the voltage at resistor is given by VR. The voltage at capacitor is given by VC. And then if you plot the phasor diagram for the purely inductive, purely resistive, we have VR here. And then for purely capacitive load, we have VC here. And then if you want to find the resultant voltage, if you want to find the voltage, it will be the vector sum of this VR and VC. Why we are drawing this, that VC in like in a downward direction, is in a negative? It's because of the phasor relationship that we have discussed in our previous video. In a purely capacitive load, your IR, your the current is leading the voltage by 90 degree. So that's why we are using that concept. And then okay, now from this triangle we can make the voltage triangle here. Again, VR is given by IR, VC is given by I times the capacitive reactance, and then again here the resultant voltage V is given by current times the impedance. Now this is called the voltage triangle, and then this one is called the impedance triangle. And then from the voltage triangle and the impedance triangle, we can determine the magnitude of the your voltage, resultant voltage V, using the Pythagoras theorem. And then you can also try to determine this phasor difference, that here is represented by the alpha using the any trigonometric ratios. And then you can also determine the magnitude of the impedance Z using the Pythagoras theorem. And then you can also determine the alpha or the phase difference using the trigonometric ratio. So if we apply the trigonometric ratio in the voltage triangle, your V is given by this expression, and then tan alpha is given by VC by VR by trigonometric ratio. Similarly, if we apply the Pythagoras theorem in the impedance triangle, you will have your Z is equal to R square plus XC square, and then you can also determine the other magnitudes, either I mean the phase angle, using the trigonometric relations, trigonometric ratios. And then similarly we have numericals here. You can try to solve it, and then if you have any doubt, let's discuss in our group chat or in an email. Now this is the final combination R, L and C series circuit. Now here the supply voltage is connected in series with the R, L and C. So if you try to draw the phasor diagram for the considering it as a purely inductive, purely capacitive and purely resistive, you will have like this. At the zero angle, at the 0 degree, we'll have the VR. At the plus 90 degree, we'll have VL. And then at the minus 90 degree, we'll have VC. And then from this, we can derive the impedance triangle or the voltage triangle like this. Here, the voltage triangle is given in this diagram itself here. We have VR in the x-axis, and then now this resultant voltage V, it can be like okay. Now in order to take the hypotenuse, in order to take the height of this triangle, from here to here, from this VR tip to this voltage V here, it will be the sum of VL and this VC. So if this is positive and if this is negative, if you are finding the sum is same as we are subtracting that one, right? So it will be VL minus VC. So this height of this voltage angle will be VL minus VC. So you have the voltage angle like this. At the x-axis at the 0 degree we have VR, and then in the y-axis we have the sum of VL minus VC. And then if we are finding the hypotenuse here, this V, using the Pythagoras theorem, then your V will be equal to root of VR square plus bracket upon this whole square, right? I think we have here. Okay, we have here. Okay, now here, now in order to consider, okay, in order to calculate the magnitude of this V, we have three cases. The first case is when VL is greater than VC. Second case is when VC is greater than the VL, and then third case is when VC is equal to VL. So okay, here, okay, this is the first case here. This is the first case. VL is greater than VC, so we have the voltage angle in the first quadrant here. And then in the second case, when VC is greater than the VL, we'll have the voltage angle like this, and our impedance angle will also get changed as per the voltage angle. And then we have the third case when VC is equal to VL. So we have the Phasor diagram like this. Now, in order to analyze the magnitude of the resultant voltage for the RLC series circuit, we have XL, when XL is greater than XC, we'll have, okay, now here we are directly calculating the impedance only. So if same concept we can apply for the voltage, how to calculate the voltage. Your Z will be equal to root of R square plus XL minus XC whole square. And then you can also determine the phase with the trigonometric ratios. And then for the second case, when XC is greater than XL, we'll have root of R square plus XC minus XL. Then you can also find the trigonometric ratios using, you can also find the phase angle using the trigonometric ratios. And then the third case, when XL is equal to XC, the applied voltage V and then the current are in phase. Now this effect is called the series resonance. Now here you have the new term. When XL is equal to XC, so your current and the voltage, the applied voltage and the current are in same phase, which means it acts as a purely resistive load. And then during that time, you will have minimum impedance. The value of Z will be equal to R. Now, this is called the series resonance. Okay, here you can try to solve the numericals using that formula. And then let's discuss about the series resonance. When XL and XC, when XL is equal to XC, the circuit will have applied voltage in phase with the current. So this effect is called the series resonance. And there are three properties that we have at the resonance. At the series resonance, we have VL is equal to VC, which means if you do the addition, summation of this VL and VC, you will get 0. And then you will have the minimum impedance in the RLC circuit during the series resonance. So your impedance, the total impedance Z will be equal to R. And then during the series resonance, you will have the maximum current in the RLC circuit, because during the resonant time, your Z will be minimum, which means you can increase the current. When the Z value is minimum, the current is, you will have the highest value of the current. So these are the three properties during the resonant. VL is equal to VC, and then Z is equal to R, and then I will be maximum. And then now when you say about that VL is equal to VC is same as that our supplied voltage VR and then the current IR are in phase. Okay, now how to calculate the resonance frequency? Now using that concept, since XL is equal to XC, then we have, if you substitute here, XL is equal to 2 pi. Now here we are just writing FR just to indicate to calculate the resonance frequency. So our previous, the original expression is for XL is equal to 2 pi F times L, right? Now that one is equal to 1 by 2 pi FR by C. Now if we equate this one, you'll get FR is equal to 1 by 2 pi root of LC. Now this is the expression to calculate the resonant frequency. Okay, now the meaning is here. Now X in during the resonant time, the XL is proportional to F as shown in this figure here. If we draw the graph between the XL and the F, you'll have that XL, the value of XL will increase along with the F. Just use again this formula. You have XL is equal to 2 pi F L, right? So if you increase the F, your L value, your X, if you increase the F, your XL will also increase. And then if you reduce the F, your XL will also reduce. So this is the XL. Here we can calculate that XL is proportional to F. And then if you're checking about the XC is equal to 1 by 2 pi FC here, when you increase the frequency, the capacitive reactance will decrease. If we decrease this FR, or if we decrease this frequency, your XC will increase, which means they are inversely proportional. So see here, if we have the minimum value of frequency here, you will have maximum value of XC. If you increase the F, you will have the minimum value of XC. And then during the resonance, if we do the addition of these two figures, here we have in the x-axis we have frequency, and then in the y-axis we have XC and XL. If we add these two graphs, you'll have like this. So at the point of intersection, it is called the series resonance frequency. And then during this time, you will get XL will be equal to XC at this point. And then, from this point, now the left side of this is called the capacitive, and then the right side is called the inductive. So from this graph, everything is given here. Okay, then there are a few numericals. We can try to solve this. And then in the next video, we're going to discuss about the quality factor. So that's it.